This is a video for MEI Core Pure Polar Coordinates 1.2 Sketching Polar Curves. Sketch of a curve shows its shape and some of its important points. Techniques we use include working out the coordinates of a few points on the curve and then trying to work out how to connect them. Consider how r changes for different theta. For instance, what values of theta give me r equals 0, or a maximum or a minimum. This is particularly useful when we've got trig functions. Finally, you could use a graphical calculator to plot it and then draw your sketch from that. We're going to look at three curves. We're going to look at r equals 4, 3 times 1 plus cos theta, and 3 sine 2 theta. We will also look at what happens if we change these values, the constants in these things, to see how that affects the shape and size of the curve. You might want to stop at this point, or indeed any other, and consider what happens next. Okay, here's r equals 4. I've no definition for theta at all. Theta can take any possible value. And so r equals 4 means that for every value of theta, as we go round here, I'm going to get a distance 4 out from the origin. And I think you can see that this will end up as a circle. And there's our final plot. What happens if r is not equal to 4 but is equal to some other value? You might want to think about that, and we'll look at that later. So let's look at this. We've got just a single cos theta in there, and so I'm going to look at key angles to start with. Every quadrant as I go around, every 90 degrees or pi by 2 radians. And I know that cos starts at 1, drops to 0, then minus 1, and then back up to 0 and 1. So cos taking those values, I'm going to get 6 here, 3 here, 1 plus 0 is just 1 in the bracket, 0 here, back up to 3, and then back up to 6. So it's going to start here, sweep round to here, and then sweep into here, and then back out to here, and back out to here. So let's just draw that in. It's going to sweep around to here and into the center, and then the other half of this curve is going to be the mirror image, and we get this funny sort of heart shape. There's the plot for you, and you might think it looks a bit like a heart shape, and in fact we refer to this as a cardioid. Again, later on we'll look at what happens as we vary these things. Our final one is 3 sine 2 theta. Now I've got sine 2 theta here, and if I want to think about every sort of pi by 2 around there, I'm actually going to consider every pi by 4. So start at 0, pi by 4, pi by 2, 3 pi by 4, pi, 5 pi by 4, 3 pi by 2, 7 pi by 4, and 2 pi. Sine, remember, starts at 0, goes up to 1, comes back down to 0, and so on. And sometimes it's useful to just sketch a graph of sine or cosine to help you through. So starting at 0, r is going to be 0. Remember, this will be pi by 2 for the sine function. It's going to be a maximum, so that's going to give me 3. That will come back down to 0. 3 pi by 4, this is going to be a minimum, so that will go out to -3, back to 0, up to a maximum again, so that's going to go up to 3, back down to 0, -3, and 0. Now we need to think about how to use -3 as a radius, and what that means is that it goes backwards down the radius, so effectively out through the other side. So my plot is going to start at 0, go out to this point, and back to 0. So looking like that. It's then going to start at 0 again, go to -3, so instead of going up to here, it's going to go down to here. And for this, I'm going to use a dotted line because I've got a negative R value, so it sweeps around this lobe. And then for the next one, it goes out to a maximum of 3 again. So it's going to go out. This is positive, remember, so I can use a solid line back to the middle. And then finally, it's in here, but because it's negative, it's actually going to end up going out to here. So again, dotted line because it's negative, and it's going to go around there. There's a tidier version of that, and you can see the dotted lobes are there. Again, we're going to look at altering these things. So let's have a look at a dynamic plot for each of these curves. Okay, there we've got a plot of r equals 4. It's actually variable this. I can change this value. You might want to pause at this point and consider what happens if I reduce that to 2. Coming down then, as I head towards 2, you can see the circle gets smaller, and there we are. You get a circle radius 2. Push it on up to 5, I get a circle radius 5. This is the next one, my cardioid. I can vary the two values. There's the 3 outside and the 1 that's inside. What happens as I vary the 3? Well, it just affects the overall size of the curve. Remember that this bracket, 1 plus cos theta, oscillates between 0 and 2. So this just allows the maximum radius to oscillate between 0 and twice that. Let's push that back to 3. What happens as I alter b? Well, that's going to affect the boundaries on this bracket. If I increase b, then it can no longer get down as far as 0, and so we see a sort of flattening out of the dent in the cardioid, the cusp as we call it when it goes to 0. If I go below 1, you start to get a loop, and actually that loop should be dotted. This package won't show it dotted. And finally, here's r equals 3 sine 2 theta. This package doesn't show the dotted line, as I said before, so this green line here is actually picking out the point P, so watch as I go up towards pi by 2. I've gone around the first lobe, and then as I go around the second part, you can see I'm actually going around the bottom right hand lobe and on round and on round there. Okay, so what does altering the values mean? Well, as before, the number outside just alters the size. If I push that on up to 5, you'll see the lobes stretch out as far as 5. And if I alter the number of thetas, we're using sine 2 theta at the moment, what happens is I increase that up to 3. Well, that's unusual. And then up to 4. Well, I've got 8 lobes there. I had 4 with 2. So why have I only got 3 with 3? And the answer is I've actually got 6, but they're lying on top of each other. And to prove that, I can show you what happens as we start at 0. As we go around the first pi by 3, in other words 60 degrees, we go around the first lobe, second, and the third, and then as we sweep on past pi, we go back round all three lobes because we're using negative values, and of course that doesn't show up as dotted lines on this plot. Okay, that was our polar plots. You might like to consider how you would do that using Cartesian coordinates. And our next video, 1.3, looks at converting between forms.